Hello, welcome to lesson 10 on variance and covariance. Some notation here. The Greek letter sigma, the capital sigma, means the sum of, summation symbol. The lowercase is going to represent standard deviation, which we're going to talk about a little bit later in this lesson. Recall the definition of the expected value of a random variable x for a discrete random variable. The expected value of x is the summation x sub I times p of xi, where p is the probability mass function of x. And so the expected value is the mean. In the last lesson, we mentioned the expected value of ax plus b. We're going to do this out a little bit more formally here. We're going to show that the expected value of ax plus b is equal to a times expected value of x plus b, where a and b are constants. So what's the calculation here when you're doing the expected value of an expression? It's the sum of the expression times the corresponding probabilities. And then in the next step here, we're distributing the p of xi times axi and times b. So we're using the distributive property here, multiplying through by p of xi. And then we'll use the fact that the summation is linear, that we can do each part separately. We can sum axi times pxi plus the sum of b times px sub I. And then in the next step, we factor out the constants here. A can be pulled in front of the sum as well as b. Now notice in this first expression here, we have the expected value of x. In the second expression, we're summing the probability mass function p, so that has to sum to one whole. So we're left with a times expected value of x plus b times 1. The sum of all the probabilities is equal to one whole 100%. And so we're left with a times expected value of x plus b. Which is what we wanted to show. I don't think we didn't use a definition in this line here. Okay. So this is a little bit more rigorous proof that the expected value of ax plus b is equal to a times expected value of x plus b. So the expected value of x is the mean, mu, of the random variable x. Let me just put that in here. This is the Greek letter mu. So the expected value of x is the mean, and that u-looking symbol is the Greek letter mu, mu. Now we're going to define the variance of x, and that is the expected value of x minus mu squared. And the notation here is sigma squared to denote the variance. And the variance measures how spread out the values of x are from the mean. We're measuring the squared, we're taking the expected value of the squared difference of x and the mean. Now, we have a slightly different formula for calculational purposes, so we're going to expand this definition out. The expected value of x minus mu quantity squared. So just squaring that out, we're going to get x squared minus 2x mu plus mu squared, just multiplying that out using FOIL or the distributive property. Then the expected value is linear. We can apply the expected value to each piece and factor out constants. So we get e of x squared minus 2 times e of x mu plus e of mu squared. Now, mu is a constant as well, so we can pull that in front. We have minus 2 mu times e to the x times expected value of x. Expected value of x is mu, though, so that becomes another copy of mu, which leaves us with a negative 2 mu squared in the middle, and then we can combine that with the positive mu squared on the end for a negative mu squared. And so probably in most cases, this is going to be a faster way to do the calculation for the variance. It's the expected value of x squared minus the mean squared. Or we could write it in the form e of x squared minus the expected value of x quantity squared. Now, taking the variance of the expression ax plus b, note it's a little bit different here than what we saw with expected value. It's a squared times the variance of x. So the addition of a constant does not have an impact on the variance. The variance is measuring how spread out the data is, so shifting the data over has no impact on the variance. But notice here, multiplying by a on x, the variance, it becomes a squared because these are squared differences here. When we get to standard deviation, we'll be taking the square root. So we're just going to do a quick proof for the variance of ax plus b. We're going to use the expected value. We're going to use properties of the expected value here. So the variance is equal to the expected value of y minus its mean squared, or y minus e of y squared. So that's ax plus b. We call y ax plus b. It's ax plus b minus its expected value, which is a e of x plus b, and then this whole thing gets squared. Now, in the subtraction here, the b's are going to cancel out. So we can cancel out the positive b and the negative b. And so we're left with ax minus a e of x quantity squared. We can factor out an a, and then factoring out of the square, it's a squared times x minus e of x squared. Again, we can factor the constant in front of the expected value, so we're left with a squared out front, and then e expected value, x minus e of x squared. But this is the definition of variance. This is the variance of x. And so we do get a squared times the variance of x, which we wanted to show. So again, variance of ax plus b is a squared times the variance of x. And then the standard deviation of x is the square root of the variance. So both standard deviation and variance are measuring spread. Both have their strengths and weaknesses in terms of when they are convenient to use. We're going to see some properties that the variance has that make some calculations a little bit easier. But the variance is kind of artificially squared. It's in different units than the original data, whereas by taking the square root, the standard deviation is back to the original unit. So there will be cases where that is a more convenient description of the spread. If we have n independent random variables, and x is the sum of those variables, then the variance of x can be calculated by adding up the variances of each individual random variable. And this does not hold for standard deviation. So this is one of the benefits of working with the variance. In this particular case, we have a property here that works for the variance but does not work for the standard deviation. If you have independent random variables, the variance of x is equal to the sum of the variances. All right, let's take a look at some examples here. The expected value and variance of the face value of the roll of a single die. So I believe we did the mean in a previous lesson. It comes out to 3.5. We'll just go through that briefly here. Again, it's summation x times p of x. The x values are 1 through 6, and the probabilities for rolling a fair die, they're all the same 1/6. And so this totals up to 21 over 6, or 3.5. Now, to find the variance, we need to find the expected value of x squared. We're going to use the calculational formula here of the variance, expected value of x squared minus e of x squared. So we have to find the expected value of x squared. So we're going to do the same calculation, but with the x's squared. So it's 1 squared times a 6 plus 2 squared times a 6 plus so on all the way up to 6 squared times 1/6. And that simplifies down to 91 over 6. And then we're going to subtract the mean that we just calculated, this 21 over 6 squared. So it's 91 over 6 minus 21 over 6 quantity squared. And that is 35 over 12, or about 2.92. So the variance of this random variable, face value for a roll of a single die, the variance is 2.92. Now, we're going to look at a exaggerated example here just to see how the variance can change. So we're taking a random variable here. It only takes on two values, each with a 50% probability. X is either 0, and the probability of that happening is 1/2, or x is 7, probability of 1/2. And so, sorry. And so we're going to have the same mean here. So the expected value of this random variable is 0 times its probability 1/2 plus 7 times its probability 1/2, which is 7 over 2, which is 3.5. So again, kind of a contrived example here. We put 50% of the probability at 0 and the other 50% at 7. So the mean is 3.5. And we're going to see a much larger variance here because the x values are not really ever close to the mean of 3.5. They're either 0 or 7 and nothing in between. Whereas in this example here, we do have x values that are close to the mean. We have a 3 and a 4 very close to the 3.5. So in this case here, the variance is going to be larger. So the expected value of x squared is 0 squared times 1/2 plus 7 squared times 1/2, which is 49 over 2 minus the mean squared. Minus 3.5 squared is 12.25. So we see a much bigger variance here because the x values are farther away from the mean in this example. So I have a much larger variance. The values are more spread out from the mean, 12.25 as compared to the previous example of 2.92. All right, a third example. A coin is flipped 3 times. Let x be the number of times tails is flipped. Find the expected value and variance of x. There are 2 to the third equals 8 equally likely outcomes. So how many ways are there to get 0 tails? There's only one way for that to happen. It have to be HHH. So there's only one way for that to happen. So the probability of 0 tails is 1/8. Now, how many ways are there to get 1 tail? There are 3 possibilities in any of the 3 flips. So the probability of that is 3/8. Now, 2 tails, we could do a combination, or we could view 2 tails as 1h, and that's also 3/8. And then 3 tails, they all have to be t. There's only one way to do that. So this is our distribution here. These are all the possible values for the random variable x and the corresponding probabilities. Notice that the sum of the probabilities has to add up to 1, and it does. We have 1, 3, 3, and 1. That adds up to 8/8. So this is our probability distribution, and now we're going to calculate the expected value and variance. So the expected value, summation x times p of x, so it's each x value times the corresponding probability, 0 times 1/8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. And that comes out to 12/8, or 1.5, which should make sense. If you're flipping a coin, a fair coin, 3 times, you would expect on average to get half heads and half tails. So that's where the 1.5 comes from. Now we're going to calculate the variance. So we need the expected value of x squared. So we're squaring the x values. The probabilities stay the same. 0 squared times 1/8, plus 1 squared times 3/8, plus 2 squared times 3/8, plus 3 squared times 1/8. And that comes out to 24/8, which is 3. And then we use the formula for variance, expected value of x squared minus the mean squared. So it's 3 minus 1.5 squared, 3 minus 2.25, which is 0.75. So the variance here is even lower in this particular example. We have a small variance, meaning that the data values are fairly close to the mean. The mean here was 1.5, and notice that we have a few values here very close to that. And notice that we have a larger probability. The probability there was higher, 3/8 there for those values. It trailed off as we went further out. So the probability is centered there towards the mean, and that's why the variance is very low here, only 0.75. All right, covariance between two random variables x and y. The covariance of x and y is the expected value of x minus ex times y minus e of y. And we have a calculational formula, expected value of xy, expected value of the product xy minus the product of the expected values, e of x times e of y. The covariance tells us how the values of x and y move relative to each other. If large values of x happen with large values of y, the covariance is positive. We have a positive correlation between x and y. If large values of x occur when y is small, then we have a negative correlation. We're going to have another video coming up on covariance. Okay, as usual, please don't hesitate to email if you have any questions or concerns.